If you've ever programmed in a low-level language like C, you've probably heard of the stack and the heap. They are two distinct regions of memory, each serving a different purpose. The stack holds the local variables used by a function. It follows a last-in, first-out structure. Whenever a function is called, its local variables and return address are pushed onto the stack. When the function returns, the entire stack frame is popped off and execution resumes from the stored return address. The CPU and compiler handle all of this automatically. But the stack has some limitations. First, the size. On most Linux systems, the default stack size is around 8 megabytes. Second, the stack memory is local to a function. While its values can be copied or passed to other functions, the stack memory itself is reclaimed automatically when the function returns. Therefore, you cannot safely pass a pointer to stack local memory. So, what happens when you need a lot more memory? Maybe you're allocating giant matrices or building large data structures. Or you need to pass the same data across multiple functions. That's where the heap comes in. The programmer explicitly requests memory from the heap to store data. That memory stays allocated until the programmer releases it. In other words, the programmer manages the heap. Now, if you've only programmed in Python, chances are you've never had to think about memory management. So, how is Python doing all of this for you? To answer that, we first need to understand what Python actually is. Python is just a language. There are multiple interpreters that can execute Python code, but the most common one is CPython, and it's written in C. So when people say Python, they're almost always referring to CPython. Now let's compare the same piece of code in C and Python. In C, when you set int x to 42, the compiler simply allocates 4 bytes for x on the stack. In Python, things work very differently. When you write x equal to 42, CPython allocates a py object on the heap. The py object is a C struct CPython uses to represent every Python object in memory. Besides storing the actual value, it also stores metadata, such as the object's type, reference count, and other information the interpreter needs to manage it. It also maintains a local namespace for every function that maps the variable name you declared to the address of the object on the heap. Because of all this extra metadata, a Python integer occupies much more memory than a native C integer. In fact, if you check the size of the same integer value, it's 7 times larger than its C counterpart. That's the fee Python charges to give you tremendous flexibility. Consider this simple code. In C, if you set int x to 42 and later switch it to the char C, the compiler immediately throws an error. In Python, however, you can seamlessly switch x to hold any value at runtime. The interpreter simply switches x to point to a completely different object. But now we have a new problem. Since every object lives on the heap, Python needs a way to keep track of them and reclaim memory when they're no longer needed. So, how does it solve this? It uses the reference count stored inside every py object. The reference count tracks how many references currently point to an object. Let's make that concrete with a small Python example. Suppose we write x equal to 420 and print its reference count. Python allocates a py object representing the value 420, and the variable x becomes one reference to that object. The getRefCount function returns the number of references to the py object on the heap. The variable x is the obvious one, but internally Python also creates temporary references while calling the function, so the reported number is slightly higher than you might expect. Now suppose we write y equal to x and print the reference count again. The reference count increases because y now points to the exact same object. Next, if we delete y, the reference count drops by 1. Notice something important here. When we call del y, Python removes the variable name y from the function's local namespace. It does not immediately delete the associated py object. Instead, it simply decrements that object's reference count. Once the reference count reaches 0, Python reclaims the memory occupied by that object. One quick note. If we had used the number 42 instead of 420, you would have seen ridiculously large reference counts. That's because of something called as small integer caching. I've already made a dedicated video explaining how that works, so be sure to check that out if you're curious. Now, as useful as reference counting is, it isn't perfect. Consider two nodes of a linked list. Node A points to B, and B points right back to A. Now suppose we delete A. The reference count of node A is still 1, because the next attribute of B still points to it. So node A isn't deleted. Next, we delete B. The reference count of node B is also 1 because the next attribute of A still points to it. So node B isn't deleted either. The variable names are gone, but the objects continue occupying memory on the heap. This is exactly the kind of situation that reference counting alone cannot solve. Python has another mechanism to handle this. The garbage collector periodically scans for groups of objects that still reference one another but are no longer reachable by your program. When it finds these unreachable cycles, it safely reclaims their memory. Since cycle detection is relatively expensive, Python doesn't perform this scan every time an object is deleted. Instead, it runs periodically. Unless, of course, you explicitly import the GC module and call the collect method. It forces the garbage collector to run immediately. For more such bite-sized coding insights, smash the like button and hit subscribe.